Live from the Creation Museum, it's Flatline. Welcome to another episode. I'm your host, Rocket Rob, with my co-host here, Danny Faulkner. Why don't you go ahead and say hi, Danny?
Hi, Danny.
Hello, guys. Thank you again for joining in with us this week. Today, we're going to be continuing our conversation about how do we prove or how do we confirm that the Earth is a globe. So, just real quick, as we're jumping online here, if you guys have any comments, again, please go ahead and put those up there. Tell us where you guys are coming from, where you're located at, and and then if there's any good questions, we'll make sure that we address that here on the show. And before we dive into more of those proofs of is the Earth a globe, I just want to really quick recap last week if you guys missed last week. So last week, basically what we did is we covered the difference between inductive and deductive reasoning, how that looks like, versus the specific, the bottom up versus the top down. We also talked about the edge of the Earth's shadow on the moon during lunar eclipses. That can only happen regardless of the time and orientation. It has to be a sphere. And we also talked about the visibility of the stars versus the northern and the southern parts of the sky as well. Talking about the North Star and the altitude that's higher in the sky at certain northern versus southern locations. And that, of course, can only be explained if it's a north-south motion along an arc. As we also talked about some of the visible constellations as well during the seasons, summer versus winter, southern hemisphere versus northern hemisphere. Also want to let you guys know as well, Teddy Bear is joining us today in the studio. So if you guys have any questions for Teddy, he is a camera hog sometimes. So if you guys have any questions for Teddy, he is here today. So go ahead and post those up. And without further ado, let's go ahead and jump right into it, Danny. Let's start off with some of these proofs that we're talking about. I know we teased a little bit last week at the end. We're going to talk about some of the ship holes and whether or not, do they disappear? Can we see them? How far can we actually see? And let's go ahead and start with that.
Yeah, but the one I want to transition from last week into this week is due to Pliny the Elder in the 1st century AD. This is a good 400 years after Aristotle. And what he said was, as a ship departs from a port, the ship will disappear hull first, eventually moving up and covering the mast as well. And reverse happens as the ship approaches. Now, I've always been a little skeptical. Could he actually see that? Because in order to start seeing the disappearance of the ship, the ship has to be at least 5 miles or more away. And it's just really pretty tiny when they get that far away. But I think he inferred that from other information. They knew at that time that if somebody was to perch a mast of a ship, they could see the land as they approached before people on the deck could. And that's the reason why they put spotters up there. Right. Also, many of these ideas come from the ancient Greeks and the Eastern Aegean, the Aegean Sea and the Eastern Mediterranean. There are plenty of islands, very rocky, hilly islands. And if you get up high start on the beach and look at a nearby island, from one island to another, you may not see that island at all or see very little of it, but if you climbed up on the bluffs on the hills, you would see much better. I saw that myself in Door County, Wisconsin 20 years ago. My son and I were on the beach. Door County is a peninsula that sticks up between Green Bay and Lake Michigan. It's got 18 miles, I think, across Green Bay to the upper peninsula of Michigan. And on the beach, all we could see was open water. We didn't see any tree line of the UP at all. But then later on, we drove up some bluffs above the beach, and we could see the tree line all the way across. And that's the kind of thing that I think that Pliny saw and realized that ships should do that. And I've taken some photographs of these myself. I don't live near a large body of water, but I have traveled there a few times. So this first thing I'm going to show you is
real quick before we go into there. I just want to say hi to Patricia Jean Shelton. She's watching from Minneapolis, Minnesota. Also, hello to Timothy Fox for tuning in with us as well. Thanks again, guys, for coming on to the show here. So, all right.
Okay, so I have here 4 photographs. These are selected from a bunch I took. This is the Virginia beach about 6 years ago, I believe now. And you can see I got the four indicated there, and you can tell the upper left, that was the one when the ship was closest. The next one to the right of it is when the ship was a bit farther out, and then the ship turned as it cleared, I think, Chesapeake Bay and was heading out into the Atlantic. You're seeing the stern, and then at the bottom, all you see is the white, that top, which is the superstructure of the ship. You're not seeing the containers anymore. In the first photograph, you can see the part of the hull of the ship. It has the NYK line. It's a major Japanese shipping firm. And I've seen their ships many times, and their letters don't go to the waterline. They're actually above the waterline. So even in that first photograph, you can see that it's at least partially blocked off by something, and that something appears to be water. And I think that's the hump, if you will, the curvature of the Earth, just as Pliny the Elder talked about. And then you've got the second window. The hull is now completely blocked. And as it gets farther and farther away, you can tell by the size of the ship, it's getting smaller. You're seeing that. And this is direct evidence that the Earth is indeed a globe. And I've done it since then a few more times. I've got some photographs here from, this was taken in the in southern Florida back, I think a year and a half or 2.5 years ago. I think this ship was heading into the port at Fort Lauderdale. In the upper left, you can barely see the back of the ship there. I spotted this. By the way, I was using in both these instances the Questar telescope, a 3.5-inch diameter. It's got a 1,300 millimeter focal length, which is a whale of a telephoto lens. That's 2.5 times the focal length of the P900 and P1000 cameras that the flat earthers seem to love so much. And that ship is some distance off. As it got closer, it not only got closer, but it also turned. It was heading into the port, I believe. And the second photo is a little later, and you can see now the front of the ship, the middle of the ship, and the back of the ship. The third photograph in the lower left there, you can see more of it. And finally, you can see much of the hull showing up. And the size of the ship, you can tell it's getting closer and closer and closer to us. So I have others I could show you, but every time I've done this experiment, every time I've done it, I get this kind of result, just like Pliny the Elder said. So my own personal experience is that I see evidence of a globe.
And obviously, this is something that you can do. I mean, if you live next to a giant body of water like this, it doesn't take anything fancy or any kind of special.
You need optical aid
consideration
to see it really well. You need binoculars or a telescope in order to see this, I think, to bring it in well.
But some basic equipment, I mean, you could easily do this yourselves. And I just want to, real quick here, HWD71 from Australia. So thanks for tuning in. That's quite a ways away there. And Timothy Fox as well from Ohio. So thanks, guys, for tuning in today.
All right. Now, flat earthers say we should use a esoteric approach. That was coined by Samuel Rowbottom. I'll have more to say about him in the future tonight. But he said you should only trust and believe what you can prove or test for yourself. Well, I've done this. I've tested for myself, and I challenge people, do it yourself as well. Yep. Now, this then begins to touch upon one of the major argument that flat earthers use. They say we see too far. In fact, one of the comments from last week was just basically that we see too far.
That's the number one.
And this goes back to Samuel Rowbottom. I mentioned him Pass that back here. He did what's called the Bedford level experiment. This was done 150 years ago. Bedford level is this flat section of water in
about 6 miles, right?
Eastern England. It's about 6 miles. It's been straightened and drained, and it's a very flat area. I'll use that term flat. Got to understand what the meaning of the context is there. And he reasoned that if he got down in the water in the lower right, you can perhaps see him in the water there with a little telescope at point A. And he's placed his telescope 8 inches above the water. And that's important because if you place your viewing position 8 inches above water, then the tangent to the Earth's surface, the geometrical horizon, will be 1 mile away. And so he reasoned that be up to 1 mile, you could see everything just fine. But after a mile, then the curvature of the Earth would seem to interfere. And indeed, he got somebody with a boat, and you can see the oars in the boat, and he's got this white flag or placard several feet across on the back of the boat. It goes up like 6 or 7, 8 feet perhaps. And he has this person to row down the length of the Bedford level. And his reasoning was, by the time he got the total 6 miles, that is 5 miles past the horizon point there, then he wouldn't be able to see it because of the Earth's curvature. The amount of curvature would amount to over 20 feet, which would more and more obscure it. And you can see that red line showing, I've drawn in there. This is an actual diagram from his book, by the way, but I added the red line, which show the light leaving that boat, going tangent to the Earth at his location. The tangents at different places are going to be different because of the Earth's curvature. And lo and behold, he reported that he could see the boat the entire way. And it turns out that is not an unusual, well, it is an unusual, but it's not a unique situation or an impossible situation, because when you have a warm spring or summer day, the water can be quite cool. Happens a lot in the spring and summer days when it's warm.
Spring and summer.
And you end up with a with a layer of air that's in contact with the water that's significantly cooler than the rest of the air. It's called a temperature inversion. As you know,
That's right.
everybody knows from grade school science, the air temperature is warmest at the surface, and as you rise, the air temperature generally decreases. Well, this is a situation where it actually is cooler. You rise a short distance, and it gets warmer, and then it starts getting cooler.
Hence the name inversion
Yeah,
there. Yep.
and temperature inversions are common in Los Angeles, for instance, quite a bit on summer days, spring days, warm days like that. So what happens is you get refraction taking place, atmospheric refraction. When refraction always occurs when light is passing from medium where what we call the index refraction is different from another medium. And when you do it at grazing angles like this, as opposed to coming down perpendicular to the interface, you get refraction. We understand this really well. There's a thing called Snell's law that governs this, and it's something you cover in optics quite a bit. If you studied optics, did you take an optics class when you were in school? Probably part of general physics that you took. I took one optics class, and we did this and a bunch of other things as well. But the light then actually, I show that straight line, it actually bends, refracts, and curves around.
Exactly.
And again, it's a well-known phenomenon. It happens. I can't say that it never happens, but I can also say that I've never seen it. And it is relatively rare compared to
Very
other.
well understood effect. It also causes the sun to rise early as well, right?
Well, it's a little different in that case because the sun's light's coming down from above, and as it does, it's coming through less dense to more dense air, and it causes it to bend down into the more dense air. It's refraction, but a different phenomenon here. It's related to density of the air, not temperature, as this lesser so temperature. So it's related, but not the exact same effect. But you're right, the sun, if you see it rising over, say, water, you're actually seeing it about 2 minutes earlier than you actually would see it rise if it weren't for atmospheric refraction. Now, they love to talk about this next example. There's a photograph here. I'm getting ahead of myself. Joshua Nowicki took this photograph. He's a very good photographer. By the way, he is not a flat earther.
Not a flat earther.
And he took this photograph of the Chicago skyline, among others of the Chicago skyline, from more than 50 miles across Lake Michigan in a state park.
Does he know that flat earthers like to use this photo? Have you seen anything?
I am sure that he's well aware of it by now.
I wonder how he feels about
This
that.
photograph right here goes back before the flat earth movement blossomed. But it's a provocative photo because some people call it the impossible photo. And when you see there's a skyline of Chicago, you can pick out some of the Willis Tower off to the left. You got the Hancock Building and the Standard Oil Tower. A few other buildings would be more difficult for most people to identify. But notice one thing, if you look very carefully, it doesn't go all the way down to the street level. There's still some cutoff occurring there. It's not down to Lakeshore Drive, which you should see, or Adler Planetarium, things like that. Right. Because there is a cutoff taking place there. Now, Joshua Nowicki is a fantastic photographer. I love his work, and he knows about optics, and he knows the conditions where you can see this sort of thing taking place. So he takes these photographs because they're interesting. They're provocative. They really are interesting photographs.
Yeah.
But most days this photograph is impossible. Don't
Not
see
as
that.
Interesting.
He knows the weather conditions. He only bothers to do this when the weather's right. And a lot of times in analyzing these photographs, flat earthers don't really handle this right. This is their exhibit A. I usually say that this Joshua Nowicki photograph. Number one, they dismiss atmospheric refraction because if they admit that it's there, then it's game over.
Yeah, it really is.
It's ironic because in other circumstances, they want to invoke all sorts of extreme weird refraction that's not supported by optics, as anybody understands. And I just think it's weird that they'll reject something that's a matter of arc minutes and yet want 30 degrees of refraction somewhere else where it's unwarranted entirely. Also, they often, not always, but often fail to consider the height of the camera. They assume that Joshua Nowicki's taking all these photographs right at lake level. But some of these photographs, like this one, he actually told you where he took it. It's on a dune in a state park. He got up a little high. So that means generally if you stand 6 feet above the water level, the geometrical horizon is 3 miles out. That's a pretty common thing. But if you're up, say, 75 feet on a dune, that is a lot greater distance now.
Oh, yeah.
It doesn't account for all this, but it does account for some of it. And then they often don't correctly compute how much obscuration you should have if the Earth is a globe. That doesn't always happen, but sometimes they do. And then they don't really really properly compute that, and also, again, atmospheric refraction is not there. So there are a host of problems with these things, and when you analyze them properly, I'm convinced that it's not really an issue. It really actually supports the Earth being a globe, as opposed to what they have to say.
Yep.
Now, I've noticed in the last few years a shift from this. They've gone more to what some people call the black swan photo, which is right here. And this was making its rounds started about 3 years ago, I think. And photograph was taken from a beach, I think near Los Angeles, south of Los Angeles. You know, you have oil platforms out there, and it has two platforms out there, Hill House and Habitat, which gives the distances from these. And he did take it. I watched the video. It comes from a video done in 2016 by a flat earther, and he had the camera on a tripod about I don't know, yay high on me, but a little above the water, so it's 6 feet or less. And he calculated that, or he has concluded that at 6.21 miles and 6.41 miles, the Earth's hump, the geometric horizon, ought to intervene. And you can see it looks like on platform Hill House that the horizon is behind it, and it looks like it is on platform Habitat. However, that's at first glance. Notice that there's a color change that takes place out there. The more I study this photograph, the more uncertain I am of where the horizon is. The first impression you get is it's beyond both of them. But notice there is some obscuration of the one on the left, platform Habitat. You see less of the platform than you do on platform Hill House. I've come to conclude that the actual geometric horizon, or the visible horizon here, is not as far back as most people seem to think, but I'll let that go for the time being. Also, there's a lot of refraction taking place. How do I know? Well, there's a boom on the left side of the photograph. You see that and see how wavy that is?
That. Oh, yeah.
And I'm going to show you another photograph here. We'll show you the same boom, and it doesn't look like that at all. That's very indicative of refraction. Let me show you the other photograph I just mentioned. There it is. Now, this was a screenshot I took from that same video. Look where the horizon is. It's definitely in front of the one on the right. It's really in front of the one on the left. You can't see any of the structure below the platform. Notice there's very little refraction because, again, you don't see that wavy pattern showing up there. Now, I got this, as I said, I did a screenshot from the very video that first photograph came from. And it's most revealing. The flat earther made this video almost 7 years ago now. It's very revealing what he had to say about it. Now, that second photograph, the screenshot I took, this is what he had to say. He said, most days, normal visibility of platforms and boats will appear they are behind the horizon curvature of the Earth.
Most days right there.
He's admitting that most of the time,
Yeah.
what he observes and what he photographs is exactly what you would expect if the Earth is a globe 25,000 miles in circumference. As far as I'm concerned, we're done here. All right? Now, this is a flat earther actually saying this. Now, what's he say about the other one everybody talks about, so-called black swan everybody talks about? Well, this is what he says. He says, once in a while, not very often, there will be days when conditions are right to see full images. He said that about, put the screen up saying this about the black swan photo. So what's he doing here? He's cherry-picking the data.
Cherry-picking the data, yeah.
What does cherry-picking mean? It means that you go through the data, you select the data that you want to accept, no matter how much of an outlier it might be, and reject the rest of the data.
That's not how science works.
That's not how science works. You use what's called the preponderance of the data. You take all of it and you look at it. And I look at this, and 99% of the photos you're going to see are going to show globe Earth stuff, I believe, if maybe even more than 99% of those photos will. And you got 1%. Well, I can accept the 99% as being indicative of what the world really shows, and then I have to address those anomalies, and I can't.
Outliers. I mean, we have outliers all the time when we're studying different things.
And then you look for alternate explanations. You want to consider what are called conflating variables or confounding variables, other things going on. As it turns out, when you take those photographs like that, where you don't see the curvature you're expecting, and those always happen on days when there's a large temperature inversion.
Right. And then just going back to that temperature, I mean, a lot of the times it's a lot more comfortable to be taking those photos during the spring and summertime. No one wants to sit out when it's cold out, and trying to take the photos during winter time and
well, I'm glad you said that because the first photographs I showed you of the shipping the NYK ship. I took that. It's been 6 years ago. It was in early November, at Virginia Beach, and the temperature when I started, I think, was 50, and it dropped to 49. Now, have you ever been to the beach when it's 50 or 49? It's windy.
Yeah, it
And
is.
I was freezing to I was really cold that day. It was not, I was pretty alone on the beach too. People didn't hang around for hours like I did. And the water temperature that day was 62. There was no temperature inversion because the water was so warm. And again, people don't generally go to the beach when you don't have temperature inversions. The temperature inversions are the days you want to go to the beach. So that already is a selection.
Yeah, exactly.
But if you
right.
want to do your due diligence, you do what I did. You go when it's not comfortable
That's the way
to
to
look
do
at
it.
those. So again, flat earthers want to talk about the outliers, and they want to ignore the preponderance of the data, and that's no way to reach any kind of conclusion in science or
Yeah, they're
anything
very
else.
selective. They like to focus on the few experiments they like and then just ignore everything else that contradicts them.
So,
Right.
so why is it that they talk about this photograph of Chicago, they talk about the black swan photo? Why do they always get results that are different from what I get? It could be that somebody is not being honest here.
That's a possibility.
I know it's not me because I know I would love to get a photograph that shows something provocative, but I've never done that. I don't live near the ocean, so I can't go out every day, but I would love
there's no
one
ocean
day
in
to finally
Kentucky.
get this provocative photo, but I don't.
Yeah.
Now, what's going on? Have other flat earthers done this experiment for themselves? I suspect very few of them have. What that amounts to is they're trusting other flat earthers.
That's what it comes down to.
Now, how do you know that those flat earthers are honestly dealing with the data? In fact, I'm convinced there's some flat earthers out there who aren't flat earthers at all. They're simply pretending to be for fun, mocking people, saying with people they could snooker in. There's a lot of trust out there that flat earthers seem to put in other flat earthers. They will trust everything that a fellow flat earther says, but they won't trust anything I say. And I find that most interesting because it's tremendous amount of confirmation bias going on, yet they accuse us of confirmation bias.
Yeah.
But there's something even more going on there. Even the flat earthers who put these up, maybe they're not really intentionally being dishonest. They call this the black swan, and I need to take a moment and talk about this. Another way of saying this is what's called the induction problem.
Problem induction.
And this goes back to a discussion by David Hume, John Stuart Mill, and Karl Popper all talked about this at various times. That we mentioned last week how in science, we do inductive reasoning, and you reach conclusions or inferences based on what data you have. But there's always a possibility that another hypothesis or another solution could equally or even better explain your results.
And just to review, inductive meaning you're implying a conclusion is probably true based on evidences and observations, whereas deductive proves your conclusion is certainly true. So that's the
Yeah, in deductive, you start with premises and you argue if your premises are true and your logic is done properly, then you reach true conclusions and you know they're true. But inductive reasoning, you don't work that way.
Right.
You have to work
bottom up versus top down.
and you're taking specific examples and trying to reach general statements. And the problem is you can never be certain that you're actually reach the right conclusion.
That's why we
on these
never
things.
use the word prove in science. You can never prove anything to be absolutely true.
You have evidence for something. If we use the word proof in science, I think we need to qualify what we mean by that. So I don't know who came up with calling this the black swan, but I understand that in Europe they had seen white swans, and they assumed
All I've seen
swans
is
were
white swans, so therefore
all
swans
swans
are
are
all
white. And that's in the case of induction. You're using every one swan we've seen is white, so they must all be white. So it's about 400 years ago, I believe, the first Dutch sailors spotted some black swans in Australia on the coast.
Australia, yeah.
And so this disproved the universal rule that all swans are white. Now, did it disprove a general rule that most swans are white? Well, no, it didn't. But it disproved the
100% certainty
universal
all
rule that it
swans
is.
are white, exactly.
Now, when we come to scientific ideas, we have some hypothesis we test. It becomes a well-developed theory or a model, or it becomes a law of some sort. And all it takes is one real good experiment to contradict that could suggest that that your understanding is wrong. And the history of science is littered with this sort of stuff. There was one idea that we had phlogiston for burning things. Well, now it was disproven by some experiments a few hundred years ago. They had the caloric theory of heat. It was a fluid. And Count Rumford was the one who disproved that with some experiments dealing with the measurements of boring out cannon barrels. So what he did is kind of a black swan. He just disproved the current thinking. So, but I think what's happened here is that flat earthers have misunderstood the black swan concept. They think, well, all I need is one counterexample and we are done. You know, if you expect to see curvature showing up on a globe and you don't see that curvature one time, that means the Earth is not a globe. Well, what about the other 99% of the times where you
can
saw
always
curvature?
flip it around. You can play that same game too.
Yeah.
You think about that.
Yeah, you know, okay, if you think it works to disprove the globe Earth, well, I can use that to disprove the flat Earth
Exactly.
because
I
I
have
just
one
showed you some
evidence
photographs.
that's a globe, and therefore flat Earth. I mean, so it goes both ways.
It
See that
should. I
double
mean,
standard.
if it doesn't go both ways, then it doesn't go either way. And I don't think flat earthers have really come to grips with that. I think it's because they really don't understand the black swan argument. They want to make it go one way and apply only one way.
Yeah.
And that's a problem.
Goes down
And
to that
and
problem of
again, can I account for these outliers? Well, yeah, atmospheric refraction, I believe, is usually the culprit in all of this. It's called the confounding variable. And flat earthers are very simplistic in the way they approach things. It's an either or sort of thing. It's either one thing completely or it's not, and they're not open to these alternate explanations. We got any more comments coming in? Do you want to?
Looks like we might have lost connection for a minute, so but it looks like we're back on. Hopefully, we didn't lose too much in terms of what we were saying. Yeah, we'll keep going. And thanks for everyone for tuning in again as well. So we got plenty of people jumping on. We got people from all over, looks like. So thanks, guys.
Okay, so the flat earthers are hung up on just one way of
Oh,
showing.
never mind. He said that he lost connection,
Yeah.
but not us. Okay,
Yeah.
so
Flat earthers are hung up on this one idea of how to measure, how to determine the Earth's shape. Their idea is you go off and you look off in the distance and you see the amount of curvature blockage that you should see if the Earth is a globe. If not, then the Earth must be flat. And they won't listen to any other way of solving the problem. Often in science, there are many different ways to approach a problem. I'm sure you're an engineer. Is there more than one way to solve a problem in engineering?
absolutely more than one way to skin a cat. That's what I always say.
And you know, sometimes the brute force method works pretty well.
Sometimes, yeah.
But sometimes you get very clever about these things. Any kind of problem in life, you can address it directly or you can do
Yeah,
it
not
indirectly
just in
many
science
times.
or engineering, anything. Yeah.
Oh, yeah. So indirect ways work out very well. And here's the problem they have. We've talked about atmospheric refraction. It's always present in the atmosphere. You can't avoid it. Now, sometimes it's present a lot. Sometimes it's not so present. Two things. Number one, if the light is coming straight down like this into the atmosphere, here's the atmosphere like this. If it's coming straight down, refraction is zero. Because any kind of stratification in the atmosphere due to temperature or due to density is going to be done in a horizontal plane, if it will, tangent to the Earth's surface at that point. And so refraction is zero. When it comes in normally, you don't get any refraction whatsoever. So when you go at angles like this, what happens to refraction when it comes in at a really grazing angle like this? It's at its maximum. Well, that's what people are doing, flat earthers are doing. They're looking tangent to the Earth's surface or nearly tangent to it, and they're looking at the situation where atmospheric refraction is at its absolute greatest value. And that's the reason why it tends to foul up these values, because we're talking now many times seconds of arc or minutes of arc and deviation of rays of light, and that can make all the difference in the world. So
Yeah, and just a side note as well, we talked about it during episode 2. That's actually a big deal in GPS as well. When you're thinking about GPS signals, you have to think about the geometry of your satellites. You don't want your satellites to be coming in at an angle like that. You want them to be a little bit more straight on. So anyways.
So if refraction is a real problem near the Earth's surface, nearly tangent to the Earth's surface, then the solution is to look at things as you look up in the sky. And this is what Eratosthenes was all about. I talked about that last week. He wasn't looking at the rising or setting sun. He was looking at the sun at noon, when it's as high in the sky as it can get. But you know, geodesy got started. Geodesy is trying to figure out the Earth's shape and size very accurately. And geodesy really got started about 400 years ago. One of the first experiments done way back then, the French did this. They measured on a meridian of longitude, north-south, And they did a very careful surveying job, measured the distance between 2 points. And then they set up a telescope at one point. Today we call it a theodolite, what you would use, which is a telescope that can go up and down very accurately in altitude and back and forth in azimuth. Surveyors use these all the time. And they looked up to the sky, a star nearly at the zenith. That the zenith is the point directly overhead. Doesn't have to be exactly the zenith, but pretty close. And they measured its altitude, and they did it along that line, north-south line, a certain distance away, at the same sidereal time. The same sidereal time means that the star will be in the same position in the sky. You don't have to do it the same night. You can do it two different nights as long as the sidereal time is the same. And when they did this, they found the altitudes were different. And the altitudes were different because you're on top of the Earth and you're looking at, I'm trying to do this, my hands are not limber enough to do it, but you're looking at one point on the Earth like this, and then the Earth's curve, and then another point, let me just grab the globe. I got a globe here, I can do it. All right, you got a globe here, and what you're going to do is you're going to look at the altitude, you're going to look at a star up at this point, near the zenith, and if you're going to go farther south, let me turn it sideways so it's south, one up this direction, one over here. The directions are not the same looking off this thing. And so by measuring that difference in altitude of a star near the zenith, number one, you don't have refraction really being a significant role. It's going to be minor at that point. You should account for it if you can, but it's going to be very small. And number two, if you know the baseline between those two, which they did, then the difference in the angle can give you the measurement of how much arc length you have there, and hence the linear distance taking the arc length divided by 360 will then tell you what the circumference of the Earth is, which is exactly what Eratosthenes did as well. And that's how geodesy got started. And geodesy works very well. You know about the oblateness of the Earth. It's because it spins relatively rapidly.
That's something you have to take account of when you're actually doing satellite design. You have to have accuracy. They're called J2, J4, all the different J perturbations. And
Yep.
That's a real thing.
Well, the radius of curvature along the equator is different from the radius of curvature at the poles. It's a little smaller, I believe. So they were actually able to measure this by looking at the stars at the same sidereal time.
So much for brutes in ancient history and unintelligent man. And
well, this was done a few hundred years ago once telescopes had been invented and instrumentation got better and better. And as far as I know, that's still a method of geodesy today. It's not really changed that much. And a good surveyor, most of the surveying the surveyors do is just small parcels. Like your yard, if you're going to sell your house or buy your house or something, you've got to do it. And at that point, assuming plane geometry is pretty close to what you get spherical because the Earth is so big. But then you have what is called geodetic surveying, which does rely upon looking up at the stars, at least historically has. And geodetic surveyors have to always account for the Earth's sphericity. And a good surveyor knows how to do that. And a good surveyor will tell you, if you don't believe me, find a surveyor and ask them about geodetic surveying. They'll say, yeah, the Earth is a globe. It has to be. Otherwise, this won't work.
Yep.
And I'm always suspicious when I hear flat earthers say, well, this guy's a surveyor and he's a flat earther. And I said, I don't think so. Because he's going to have to deny a good deal of his education that he has on this to do it.
Yep, exactly.
Now, so you work away from the horizon as much as possible. You try to work at the vertical of these things. And this is kind of a review of last week. I showed you the circular path of the stars throughout the sky. That's a photograph I took in Arizona a few years ago. You see Polaris there at the middle, and that angle is going to change, as I pointed out before, every minute of arc you move on the Earth, that's about 6,000 feet. It's one minute. It's one nautical mile. You get 1 minute of arc of change in the altitude of Polaris or some other star at the same sidereal time. That's 69 miles will give you 1 degree. And I've tested this myself. I travel, as I said, and as I do, I actually check these things to see what they look like. Let's go back to Eratosthenes. I want to do that in more detail. Got the slide here of what I did last week. I'll go into more detail of this. Eratosthenes originally was at point B, or he knew at point B, down in southern Egypt near modern-day Swan. The sun was directly overhead. But he also knew at Alexandria, where he lived at point A, the sun was never directly overhead. I should say at point B in southern Egypt, the sun was directly overhead at the June solstice at local noon.
Yeah.
So he doesn't
Local noon,
experience.
and he could see it's in the bottom of the well as well.
Yeah, that was the reason why he knew that. The bottom of the well, you could see the sun, you could see the bottom fully illuminated. Normally, you can't see the bottom of a deep well because it's in shadow. But at any rate, it goes back to Alexandria, and sometimes people dismiss this. I think Carl Sagan may have been the first to do this, calling it sticks in the sand. It was more sophisticated than that. He leveled an area. He put up a gnomon, which is some sort of post or tower. Could have been stone, could have been obelisk, could have been wood. We don't know. But he built a gnomon of known height, because since he built it and designed it, they were good engineers. He built and designed this thing, made it perpendicular to the ground, and he waited until the June solstice at local noon. What he probably did throughout the day is he tracked the shadow as it moved across the ground. And when he got to local noon, the shadow was the shortest length, pointing northward, and he measured that length. And from that length of the shadow and from the height of the gnomon, he was able to use trigonometry to calculate then the angle theta, showing there at point A. That's how much the sun was away from the zenith. We call that the zenith distance. And he's expressed it as 1/50th of a circle, which is like 7.2 degrees.
7.2 degrees, yeah.
Which is, if you look there, we've got two lines. The sun is off to the right. And the line there, that black line, is the direction of the sun. The bottom line at point B is the direction of the sun. The sun is so far away, it doesn't really, their lines are basically parallel coming in. They deviate slightly from being parallel, but if you calculate it, it's extremely small compared to what you're measuring. It's orders of magnitude smaller than the angle you measure. So you've got effectively two parallel lines. You cut them with a transversal. You know that one angle's theta, the other angle of indicated is theta as well. And that theta happens to be the difference in latitude between the 2 points. If you know the distance S between the two, which it was surveyed, he knew that.
Yeah, he knew that. Yep.
So then he took that 50th of a circle, divided it into 60, and he gets the circumference of the Earth divided by 2 pi, and you get the radius. And his value is pretty close to the actual
within
value.
like 0.5% of the
Well, it
modern
depends on
value,
what
right?
it depends on what stadium he used. They used a unit called stadium. If he used the more commonly used one, his value is about 20% off. But if you use the less commonly used one, it's 0.5%. Doesn't matter to me which one he
But
used.
still, I mean,
got a good
that's
result. Yeah.
20, yeah, it was like 25,000 miles, give or take some. And
So people have been doing this sort of thing for a couple thousand years, but it was really went to a whole new level with the invention of the telescope, and they began doing this sort of work, doing geodesy. It's been done many, 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 many times.
a lot of people have done it.
And again, preponderance of evidence, and it's not the sort of thing that it's the sort of thing anybody can do if you want. Now, flat earthers say, well, this thing that Eratosthenes did could be interpreted in terms of a flat Earth, and you know what, Rob? They're absolutely right. So what you have here is, I put the sun there, the yellow ball there in that diagram, and it's some height h above the Earth. Their model, they have a flat, round Earth, and the sun goes in circles around the north celestial pole like this every day. That's fine.
And real quick, just on that point, we actually had a comment that talked about how the flat earthers account for time zones and the different times, for example, East Coast, West Coast. And I think you kind of hit on that as well. That's basically how they account for it, right?
Yeah, they say that the sun is like a spotlight shining down, so it's a cone.
Yeah.
So as it goes around, it shines over some area, not in others. So they'll, in this model, the sun can never actually pass below the horizon because it goes in circles, but it's a spotlight, as I said. And then they invoke weird
And
atmospheric.
they do that to try to account for the time zones,
Yeah.
basically. That's why.
Yeah,
that's
so
what
the sun is up, let's say it's up here, and it's also up in California, but it's closer to us, so it's closer to noon than it is in California, 3-hour time difference. That's how they do it. They have an answer for it. It's not a very good one, but
not a very good one, but that's
their
what they
answer.
got. Yep.
So the idea is there's some height h, and I don't care how high the height is. Other different flat earthers have said it's different heights. That's what Rowbottom did. He said it's like, I think, 3,200 miles. Other flat earthers have got different values. And here's
Yeah, they're kind of all over the place.
well, here's why. Because I got to set up again, reinterpreting Eratosthenes. Again, here is how I would understand what Eratosthenes did. You got point B and you got point A, and you're going to measure the zenith distance, the zenith angle there of the sun. Well, do it on a flat Earth. Your point B, the sun's directly overhead at noon, and it's a height h. And again, we don't know h yet, but we can find it out because if you go to point A, which is Alexandria, and you measure that angle theta, now actually what he would have measured would have been the complement of that angle, which would be the angle up at the upper right opposite of that. That's immaterial.
We're
Once you
back
know
to your
one,
geometry days here.
once you know one, you know the other. And so you can apply trigonometry if you know the distance s between the two, and we can survey that. Knowing the angle, then it follows using the arctangent.
Any homeschool kids watching, you guys can do this at home
That's
as well.
right. And you can find the
Solve
height h.
problem.
So yes, flat earthers, they can explain the difference in elevation of the sun at noon on a given date from two different locations located north-south. However, I've heard flat earthers say that many, many times, but I've never heard them take it to the next step, or rarely heard them. In the first incarnation of the flat earth movement over 100 years ago, they did. And there's a reason why they don't talk about it today, because, as I said, if the earth is a globe, then you can use those measurements to find the earth's size, the radius or circumference. If the earth is flat, as the flat earthers say, then you can use the same data to determine the height of the sun above the earth. And if you do this consistently, if you repeat the experiment different times a year, different locations, you will get different values.
Yep.
And
That should be a big red flag there.
big red flag, you get inconsistent results, which tells me when you do it with, assuming the earth is spherical, you get consistent results within the errors of the measurements. If you do it though, and you get interpreting it in terms of flat earth, and you get really discordant values that are well outside the measurements errors, then it tells you you've made a mistake somewhere.
Not going to roll. See what I did there.
and obvious to me is the assumption is the flat earth. So if you do the Eratosthenes experiment once, it doesn't prove anything except that you get a measurement of either the height of the sun or the size of the earth.
Exactly. Yep.
But if you repeat it again and again and again, what, by the way, science is all about repeatability, you get inconsistent results if the earth is a flat, and you get consistent results if the earth is a globe. That in itself collectively is very powerful evidence, proof, if you will, that the earth is not flat. We can disprove the earth being flat very easily from all of this. Now, this, as I said, this is the sort of thing a person can do on their own, and I've done this. If you want to know more, I have an article here on our Answers in Genesis website.
Yeah, this is something you do. I mean, basically, just what you need: a yardstick, you need a tape measure, and just go out and do it on one of these solstices, and
or other dates, if you will.
Yeah.
But anyway, this article here called Eratosthenes Reconsidered. I did this experiment a few years ago. And what I did is I went out, I believe, on the winter solstice, and I measured the length of the Earth's shadow at local noon, and I knew so I say winter solstice, I mean the December solstice for us.
Solstice, yep.
And I knew that the sun was over top of the latitude minus 23.5 degrees, south 23.5 degrees. And knowing 69 miles for each degree of latitude, I could calculate how far I was from the Tropic of Capricorn. And that gave me my S, which I put in my equation, and lo and behold, I got a height for the sun in the flat Earth model. I also was able to calculate the Earth's size in the spherical Earth model, and I got something close to 4,000 miles. I forget what my value was for the height of the sun in the flat Earth model, but it was different from what anybody else got. Rowbottom got 3,200. Somebody else, some other flat Earther in the past got like 800, some others got like 1,200. It's all over the place.
Yeah.
And if you just repeat this experiment, it's very clear evidence. And science, again, is about repeatability. A lot of flat earthers try to talk about the scientific method, quote unquote, and about repeatability. So you can do that. You can go to the website there and just answersingenesis.org and search for, if you just look for
type in Eratosthenes and
Reconsidered,
search bar,
and it'll come right up in a hurry.
Come right up, yep.
Now, I'll show you a picture. I got a last slide here showing my setup that I did at home. This was a year or two
there
ago.
you go.
And what I did is I got a yardstick, and I taped it to a little wooden box. I needed something kind of heavy. I tried different things. I tried cardboard boxes with weights in them with different yardsticks. And I measured and I got this at local noon, which for us is around 12:45, 12:50. And I had it set up for a couple hours. I was measuring the length of the shadow, and you can see the tape measure I got lying there. I don't have a close-up of it, but you can see the shadow goes almost all the way to the end, all of a sudden becomes bright yellow. That's the end of the shadow. And the end of the shadow is a little fuzzy because you've got a penumbra there, so you got to kind of shoot the middle of that. Yeah. But I was able to get the length of that shadow, and I've done it other times. I've measured it on different times of the year, like the June solstice, and I've measured it at other seasons. When I've traveled, I've tried it in other places, and every time I do it, I get consistent results for the Earth being a globe, same sort of measurements in and time out. Yeah. And flat earthers aren't aware of the fact that that they get inconsistent results if they're not aware of it. I mean, if they are aware of it, they're not letting on. And they don't take the science to the next step. They say, well, we can explain that observation on flat Earth. Yes, you can. However, look at the details.
Yep.
And that's the problem that I see with this sort of thing.
And then just speaking of this, one of the things, sometimes you'll hear from flat earthers as well, Eratosthenes, he was assuming the earth was a globe to begin with, but obviously, or they'll say things like, he was trying to prove that the earth was a sphere, but actually it went before that.
Yeah.
People at that time, Eratosthenes already knew that the earth was a sphere, so he was building off of what was already known. And that's what we do all the time in science. We build off of what we already know to then.
Well, I think that many flat earthers, that I've heard them talk about the scientific method, how science is done, and it's a very stilted. We maybe should talk about this in a future program. They got this idea that you got observation, you develop a hypothesis, you develop an experiment, you either prove or disprove a hypothesis, and then you're done. You put it on the shelf and you never use it again. I don't see how, but see, science is about applying what you already know. There are many, many things we know. We can build upon that. You don't have to reinvent the wheel every time. So you're right. When Eratosthenes did his experiment, he was assuming the Earth was a globe because that had already been established.
Yes, it had already been established.
And many people get this wrong, by the way, including Carl Sagan. I think Neil deGrasse Tyson, he's quoted on this. They sometimes show videos of Carl Sagan. And they're talking about Eratosthenes and saying, he's showing the Earth as a globe. No, he didn't. He was measuring it.
Measuring.
It's called metrology, and that's a part of science as well. Let me go on that for just a minute. The way flat earthers would have it, unless you got a hypothesis you're testing with a cause and effect relationship with an independent variable, you change and all this kind of stuff, and look for a change in dependent variable. Well, that's nonsense. Many of the physics labs I had my students do, we would measure properties of things such as density. I had to measure that of different substances. You could use it to identify things. We measured things like electrical conductivity. We measured coefficients of expansion. We measured specific heats of substances. That is all part of science. And it's building upon stuff you've already done. And I don't think most flat earthers understand
I don't think they do.
how science really works. That's very much a part of how we do science. So Eratosthenes was building on it. He wasn't proving the earth is flat. He was measuring, but if we repeat that Eratosthenes experiment, we get the same results every time with the globe earth. We get inconsistent results with flat earth, and that leads to a very good scientific conclusion. The earth is not flat. We have abundant evidence just from that alone that the earth is a globe.
Yep.
And it's just amazing that you can't get flat earthers off that one
Slam
note.
dunk.
Well, they want to talk about looking along the horizon. We see too far, but why are you looking up in the sky to look at the ground to see what shape the earth is? You should be looking at the ground, not up in the sky.
Yeah.
And they said they made the comparison. You be like looking at the ceiling of a room to see what the floor is like. Well, I've been in some rooms that had mirrored ceilings.
It's actually a good way to do it.
Yeah, I can't see what the floor looks like on the other side of the table from me where you're sitting.
You have a limited perspective.
That's
if
right,
you look
because
up,
the table's in the way. But if there
You
were
have
a
a
mirror up there, I
reflective
could look down and I
surface,
could see easily what's going on. You probably can't see from your side of the table if I'm wearing shoes or not.
By the way, he's not wearing shoes today.
Well, how do you know? You haven't checked, have you?
I did earlier.
But if there were a mirror, you could see very easily. So there are circumstances where looking at the ceiling to see what's going on the floor would make a lot of sense.
Or if you're at the gym, for example, and you're working out and you want to check your form, you're going to look at the mirrored wall in front of you to figure out to make sure you're doing your curls right or whatever else you're doing. I mean, obviously, you're not staring at yourself. You're staring at the mirror because you have a better perspective,
And
better angle.
That's the reason
that
why
way.
they put mirrors on the walls in a lot of
Exactly.
gyms. So good point. I like that. I'll steal that if you don't mind. Got a couple quotes here, a couple comments coming in.
Yeah, so we got plenty of ones here. So I think there was actually a comment. I don't know if you want to address this as well. So someone was wondering, do flat earthers believe that other planets are also flat? What's the consensus?
There is no consensus. From what I read, they don't really care. They can see they're round through a telescope. That doesn't mean they're a globe. So they're kind of split on that they could be round, flat discs. Some think they're globes. That's fine.
Yeah.
But they're not really ardent about that. Well, they're not going to die on that hill.
Yeah, they're not going to say one way or another. Okay, so, and then as far as some of the comments we received last week as well, I think we had one that talked about, you can't, we can obviously see too far is what they're saying. So hopefully that everything that we've been talking about today, hopefully that's been helpful for you as well. I also just wanted to point out a few of the comments that we got from last week as well. So Dan Garcia said, "Flat Mars, that's hilarious." So I wanted
Your
to,
shirt last
yeah,
week.
I had the shirt last week
We
that
should
said
talk about
Flat
our.
Mars
We should
Society.
say we should have our shirts here. You've got.
Yeah, so the one I'm wearing today is Round Earth Society, and it says circa 500 BC. You guys can see that. So that's something we talked about during the introduction episode, and so there you go.
Mine's a Bible verse. Would you read that for me?
That is, I can do all things through a verse taken out of context. First Opinions 3:16.
Yeah. And we've been wearing different T-shirts
Yeah.
every week, and I'm starting to run out of relevant T-shirts.
too.
So we might have to recycle or go to maybe I may wear my Clemson shirt.
Yeah.
Depending on how the bowl game goes, the Orange Bowl in a couple of weeks.
Yeah, we'll see how that goes. That's true.
Anyway, mentioning if you look for more comments if you have any more, but
Yeah.
I want to point out we're going to take a couple of weeks off here because
We
we have
are.
Christmas coming up. So our next show is planned to be on the 3rd of
June
January.
3rd, so we'll be back June 3rd. So
January 3rd.
I'm sorry, June 3rd would be way far.
Yeah, January 3rd. And we're
January
gonna,
3rd, so we'll be back.
and our plan is to continue talking about some of the arguments that flat earthers put forth. I talked some tonight about the
Yeah.
main one, the Exhibit A, we see too far, and the answer is, well, sometimes we do, but usually we don't.
Yeah.
So the earth is not
Right.
flat.
And so I think we're also getting quite a few comments as well, Danny. If we want to just rehash again why we're doing this show.
Yeah.
What's the reason?
Well, again, I think the flat earth movement is a threat. I think it's got some cult-like properties to it. I can see we can talk about that sometime if we wish. People mishandle scripture, I believe, to make it fit the flat earth, and the evidence doesn't support it. And, I think I'm uniquely qualified as an astronomer and as somebody who has some Bible education to address some of these issues. But, here at Answers in Genesis, we are a biblically based ministry.
Yep.
We hold the authority of Scripture above all. And simply put, the Bible doesn't teach the earth is flat.
That's right.
People get that wrong frequently. Or critics say that, and then professing Christians actually pick up that criticism and wear it as a badge of honor somehow.
Yeah.
It's not in the same league with passages that very clearly tell us that God created the earth in 6 days. The Bible couldn't be more clear than that on that issue, but the cosmology of the Bible is not clear at all. It doesn't tell us the earth is flat, it doesn't tell us the earth is a globe, it just simply assumes that the earth is here, and it's kind of us to maybe fill that in a little bit. It does not go against Scripture at all, and that's what we're all about here, authority of Scripture
Yeah,
and
we are a
getting that
biblical
right.
authority ministry, and we think that people that are trying to impose their ideas on the text, I mean, that's something we talked about in previous episodes. It's that proper way of reading in context, and we're looking at these different biblical passages. Hermeneutics is the word, and we actually have something on our website if you guys want to learn more about that, how to actually read the Bible biblically in terms of eisegesis versus exegesis. Essentially, all that means is reading into the text versus reading out of the text, and that's actually a big thing too. A lot of the times that we here at the ministry, we get accused of all the time is, we believe in a young earth, we believe in 6-day creation. Why aren't you guys also believing in the flat earth? But again, like we said before, those are two different categories. The Bible clearly talks about the earth, the universe, everything around us being thousands of years ago in those 6 days. Whereas, like Danny was saying earlier, the Bible does not say that the earth is flat. In order to believe that, you have to then read into the text in order to have that happen. And again, it also talks about that observational versus historical science that we talked about before, in terms of evolution, millions of years, that's basically taking the facts in the present and then trying to come up with a story, draw conclusions about the past. Versus observational science, we can observe, test, and repeat in the present. And so when we look at the shape of the earth, this is something we can do in the present. And so I want to make sure that's something I think we repeat every week, but I think it's worth mentioning every week as well, and repeating this every week. And also we're also getting letters on a monthly basis as well in terms of families, having to deal with this, and we have different spouses, and so again, it is tearing apart families, and that's why we're doing this show today, because we love our neighbor. That's what it comes down to, and also just remaining curious. I mean, let's remember to remain curious, and let's continue to look at creation all around us, and like the Bible says, the heavens declare the glory of God, the skies proclaim His handiwork. So.
Yes.
All right. Anything else from Teddy Bear? I know Teddy's been kind of silent over there. If he wants to say any words
He's been
before we
saying
end.
quite a bit tonight. I think he's.
I think only Danny can hear him because I always try to talk to him. He's just a
Oh,
silent type of
listen,
dude,
I'm
but
sure some people in the chats will beg to differ. They've heard him saying some things tonight.
yeah,
So.
he's usually a camera hog, so we had to kind of keep him away. So if you guys have any questions at all, also,
Tom had some photos I might want to share where
yeah,
Teddy's been
yeah,
with me.
Teddy's been all around all around the globe kicking.
There he is, Stonehenge.
There you go.
Yeah, he's a traveled bear. That's not been photoshopped. He was actually there, folks. There he is that's a size of a Mercury spacecraft. That was at a space museum we went to. There's some people who'd like to send Teddy into orbit, by the way. And there he
Make it
is.
happen.
That's my son and Teddy. Got a funny story I don't want to share with you here, but we got him a chainsaw for Christmas a few years ago. And you can see that Teddy is instructing my son how to use it. And you can see my son is very attentive to, and Teddy's is a know-it-all. He knows how to work chainsaws. And if you need some help, he knows he's wearing his backwoods sort of stuff there. So he's kind of an expert in a lot of things. There he is with one of the pet lions, baby lions I visited with in South Africa several years ago.
And so, yeah, we actually have a.
Oh, that's at Cancun.
Yeah, there you go. That's awesome. That's a good one. At Cancun on the beach.
So he's
So we
been
actually got a
around.
question for Teddy here. What is Teddy's favorite fruits?
Favorite fruits?
Yeah.
I don't know. Teddy, did he comment? He says he likes them all. So
He likes them all.
yeah.
Okay.
I'm sure some other people here have heard him say that. I'm sure some comments go, yeah, I heard Teddy speak. Not everybody can hear him.
Yeah,
apparently,
I
but,
think it's just Danny.
yeah.
Danny has conversations with him all the time. It's
Well,
great.
no, remember back in the spring, he wasn't talking to me for a while.
Oh yeah, that's
So,
true. Yeah,
so.
yeah. You just, I guess, didn't have enough cheer wine. So I don't know if you guys know this, but we didn't have cheer wine this episode, and we're gonna blame it on our producer Tom. He forgot to get us some.
Oh.
He's at home, decided not to join us today in the studio.
It's his
so
fault. Whoever's not
it's
here
his
gets
fault.
blamed for everything.
We're
you know?
gonna blame him for no.
But at least
no
Teddy
cheer
showed up
wine.
this week. So next time we'll come back with cheer wine, hopefully with Teddy, if I remember everything.
Mm-hmm. So next time we'll have cheer wine, so
if
we'll play our
Clemson-
game.
If Clemson wins the Orange Bowl, I may wear my Clemson shirt.
you go.
The Orange Bowl is, I think, on the 30th. So we'll be 4 days later. If not, I'll just quietly not say anything.
Sounds like
and wear some other
otherwise,
shirt. Yeah.
yeah, otherwise, yeah. So Tom said he's actually out sailing in search of an ice wall. So we'll see if he comes back or not
Yeah.
for that. But again, also, I think we mentioned this before, but I think it's worth repeating. Our goal is to really reach out to those who are honestly searching for answers on this movement, this flat Earth movement. And again, it's not for someone who doesn't care to listen to any evidence, who's already maybe convinced in their mind that the Earth truly is flat. This show is really about for those that maybe have a friend or a family member or themselves. They're looking for answers on this subject. So and that's why we're out here, guys, as well. So again, thanks for tuning in, guys, as well. We will be back again, like Danny was saying, in a few weeks from now. January 3rd, I believe, is when we'll be back. So we'll be taking a 2-week hiatus, but we'll be back then with Teddy Bear, myself, and Danny Faulkner. So yeah, and make sure you guys also check out Danny's book in the meantime, Falling Flat. It's available on our bookstore if you guys want to get a head start before we get back into our usual weekly routine. A lot of the stuff that we've been talking about over the last few weeks is really good detail in this book, and Danny does a really good job just explaining it from a really basic level, so really anyone can understand it. You don't have to have a PhD in astronomy to understand a lot of these arguments. So again, definitely encourage you guys to check it out. We sell it in our online bookstore as well as the Creation Museum here. If you ever want to come on down to Petersburg, Kentucky, and
we also have articles on our website, over 30
right.
now, blogs
Answers
or
in
articles
Genesis.
about Flat Earth Movement. You can find those just by typing Flat Earth in the search there. It's pretty easy to find them.
yeah, so we actually just got a comment here before we end. They said, I found cheer wine in Texas and got a 4-pack to try. Delicious. Thanks for showing that. Enjoy the instruction against flat Earth argument. Have needed the information for discussion. Well, thanks again for tuning in, and I'm glad it was helpful for you. And we're very glad that you discovered cheer wine.
Yeah,
So-
yeah, really good stuff. Get you on Clemson, we'll be in good shape.
Yeah. So Merry Christmas and a Happy New Year
Yes.
to everyone. And yeah, we'll be back again a few weeks from now. And thanks again, guys, for tuning
I
in.
got one last thing to say.
Okay.
Besides Merry Christmas and Happy New Year. Good night, Tune.
All right. Bye, guys. Have a Merry